So, the inclined plane also exerts an upward force perpendicular to the surface, and if you remember from before, we call that the normal force. And normally the normal force, all it is if you have an object in contact with the surface, the normal force is perpendicular to that object, to the surface. So if you picture our ramp scenario that we've started building, in our ramp scenario here, we have our perpendicular force that's going perpendicular to the surface. Well, the normal force would just oppose that altogether. And so looking at those components, we can see that the two of them should add together to equal 0 as long as that ramp stays, or as long as that crate or box or object stays steady on that ramp. It doesn't fall through the ramp or it doesn't lift off the ground. Then in that case, the normal force and the perpendicular force would have to add together to equal 0. So in this next scenario, we're going to take a look and see what happens with the idea if we have a frictionless problem. So if there's no friction between the trunk and the plane, the only force along the plane would be the parallel component. And so the parallel component in this case would be W sine theta. And keep in mind, this whole scenario here is talking if we have a frictionless plane. So according to Newton's second law, we also have that acceleration is equal to force divided by mass. So if we wanted to figure out how Newton's second law applies to the parallel component of this, then we could just substitute in this value in for the acceleration. So acceleration would then just be W sine theta over m. So you see where I had the parallel force above, all I did was I just substituted in W sine theta. So what we know about weight and mass, the weight to mass ratio is constant for everyone near the Earth's surface, because we know that weight is really just equal to mass times gravity. So weight over mass, we can take a look at that because we can divide by mass on both sides here, and we can have weight over mass and realize that that just equals the gravitational pull. So really, gravity is equal to weight over mass. So then, if I can substitute gravity in for this, then acceleration is really just gravity times the sine of theta. And that will tell me the acceleration of any object on a ramp if we can assume that we have a frictionless condition. So, as the plane starts to become more horizontal, the acceleration approaches 0. It's becoming flat, so it's not sliding up and down the ramp. When the plane is tilted more vertically, then the acceleration approaches a value that's closer to gravity or closer to that 9.8. So here's an example problem. I'll get you to pause the video and try it out and come back when you're ready. Okay, so a 562 Newton trunk is on a frictionless plane inclined at 30 degrees from the horizontal, and it wants us to find the acceleration. Well, the acceleration is really just equal to g times the sine of theta. So the acceleration here is going to be 9.8 meters per second squared multiplied by the sine of 30 degrees. So my acceleration in this case, sine of 30 is 0.5, so it's just half of 9.8. It's going to be 4.9 meters per second squared. And so, what's the direction, or which direction is it heading in? If you picture a trunk sitting on a ramp, as soon as it starts to lift, if that angle increases, it's going to go downward, and it's going to go parallel to the ramp. So a couple pretty important pieces there just to take away. Now, our last part says usually we have friction between the incline and the object that's on it. So if the object doesn't move on the surface, then that's known as having static friction acting on that object. And so static friction in this case, we actually touched on a little bit last year, and so we'll just need a little bit of prior knowledge just to kind of see what this is. Now, when we reference static friction, we reference this idea of the coefficient of static friction. And so coefficient of static friction is a coefficient of friction in general, and this is something I don't expect everybody to know right off, but maybe to recall from before. The coefficient of static friction is just mu. Okay, that U, or almost looks like an M, and it had an equation for it. So we could say that it was equal to the force of friction over the normal force. Okay, so that was our equation when we take a look at calculating the coefficient of friction. So how does that work when we have friction on a plane? When we have an object that's sitting on the plane and it's not moving. So if it's not moving and it's static, then what we could say was the static coefficient of friction was equal to the static force over top of the normal force. Well, what do we know so far about our ramp? So let's picture our scenario. What we have here. We have a box or an object sitting on a ramp. We know that we have a normal force going perpendicular to the ramp. And we know the thing that opposes that is the perpendicular force. So the normal force goes perpendicular to the ramp, and the perpendicular force is being pulled down as the component of the weight. So what about the force of static friction? What's opposing that? So the ramp's natural direction is to be pulled in this direction, right? Is to be pulled down this way, which is what we called here as the parallel force. So the static friction is going to want to oppose that. It's going to want to go in the opposite direction to what's there. And they should equal each other if the object is not moving. So the force of static friction and the parallel force should add up to equal 0 when the object is not moving. So that means that the static force is really just equal to the parallel force, just in opposite directions, the same way that the normal force is equal to the perpendicular force, just in opposite directions. So I can substitute those values in and say the coefficient of static friction, instead of writing the force of static friction, we know that it's the magnitude of the parallel force, okay, the value of the parallel force, over the normal force, and the normal force is really just the perpendicular force. So we know that the coefficient of static friction, because we know both of these values, is really W sine theta over W cosine theta. The weights are going to cancel out. And really what I can see here is that the coefficient of static friction is really sine theta over cos theta. And then there's this idea of a trig identity. And so there's a trig identity that says if you take sine theta over cos theta, you get tan theta. Okay, sine theta divided by cos theta gives you tan theta, which means that that is my coefficient of static friction when the object's not moving, sitting on a ramp. So really, it's taking whatever the angle is for the ramp, and then tan theta would tell you what its coefficient of static friction is, which makes it a fairly easy equation to use, given the amount of work that goes to show what it is. So there are a couple problems for you to try to go through, 23 to 26, and then after that, we're going to start to get ready for the test review. So